So, in last class we studied that we require gate pulse or gate voltages or current to trigger the SCR. In the sense, we need to apply positive voltage in between gate and cathode to turn on the SCR. So we also learned that we need to apply the gate voltage until SCR completely turns on, or else until anode current of an SCR is more than latching current. Once the SCR is completely turned on, means anode current is more than the latching current, we are allowed to remove the gate current, or else we can stop supplying the gate current. But SCR remains in on state. So summary is, to turn on SCR we need to supply a gate current for a short duration until SCR completely turns on, or else until in a junction J2 full amount of carrier flow is established, or else I can say that until the anode current of an SCR is more than the latching current. Once it is achieved, means once the anode current is more than the latching current, or else once the SCR is completely turned on, or else once the carrier flow in the junction J2 is completely established, we are allowed to remove the gate current. So that's the reason we need to apply the gate pulse for a short duration, means short duration voltage pulse or current pulse we are using, or we are supplying to the gate terminal to turn on the SCR. Means pulse means short, not a continuous pulse. Gate pulse we are applying. We can also apply continuous voltage to the gate current, no problem, but it is not required. Okay, so to generate the gate pulse or voltage pulse, to generate the pulse which is required to fire the SCR, we need to generate. So some circuit is required to generate such voltage or current pulse. Such circuit is called as triggering circuits or else firing circuits. So we use these two terms, either firing circuits or triggering circuits. The job of a firing circuit or triggering circuit is to generate a voltage which we are going to use to trigger the SCR or to fire the SCR. How we can trigger the SCR or fire the SCR? By applying a positive voltage in between gate and cathode. That whatever voltage that is required to connect to the gate and cathode, that voltage is generated using this firing circuit. Okay, listen here. First we will study R triggering circuit or R firing circuit. This is very simple one. Listen here, this is our power supply Vm sin omega t. You assume that it is coming from our mescom or else a socket of which is mounted in your wall. Okay, or else it may be coming from this secondary of your transformer, if at all you are using a transformer to tap a voltage. So this is sinusoidal, its nature is sinusoidal, so that's the reason I am describing using Vm sin omega t. Okay, you can see here such a voltage, its maximum amplitude is Vm. Okay, Vm. So this is connected to load. Yeah, it is connected to load. What are the loads? Loads may be your incandescent bulb. Yes. So to this load we have connected. It's not incandescent bulbs requires AC. You consider some DC load. It is some small DC motor or else some heating coils. Okay. And this is SCR. Okay, listen here, this is just this circuit will pass supply to the load only in positive half cycle, in negative half cycle there is no provision here to give supply to the load. So the such kind of half wave circuits are rarely used. Okay, practically it is only for analysis purpose, so you can consider any loads. Okay, remember this is a equipment, any equipment, and this is our power source, and here this is our switch. Power circuit consists mainly three parts here: this source, load, and switch. This switch, when it turns on, when in a positive half cycle, surely this anode is made more positive than cathode. Then so anode is made more positive than cathode. Then so when we apply voltage to the gate terminal, so this turns on, this SCR turns on. So what we understood here is we need to apply a voltage to the gate terminals in between gate and cathode. So we require voltage. So to generate that voltage, this circuit, these components are used, this circuit structure is used. This is mainly firing circuit. This is mainly firing circuits. Okay, or else I can say that triggering circuit. We'll see how it works. Okay, here you can see here in a positive half cycle, anode is made more positive than cathode. J1, J3 is forward biased, J2 is reverse biased. So no current is flowing in this way, correct? Because we are not given any power supply here. Initially there is no voltage because yes. Okay, see, then all amount of current is means because of this voltage the current is passing in this direction. When the current is passing, it is passing in this direction. So we need to analyze this circuit now. Okay, so I think listen here, this you keep in mind, this is very this load resistance value is very less, like 10 ohms, 10 ohm, and this resistance value is very high. This resistance value is very high. This is also nominal. Okay, you can say that it is in terms of case, and this is also case. Okay. So when kilo ohms of resistance is here, kilo ohms of resistance is here. If this is in terms of volts, volts divided by kilo ohm, what happens? Milliamps of current is flowing here. Only milliamps of current is flowing here, or fraction of milliamps. If it is total resistance is 10 kilo ohm, 0.1 milliamps of current is flowing here. If it is at 1 volt, if it is at 10 volt, milliamps of current is flowing here. If it is at hundreds of volts, still less, small current is flowing. Okay. But summary is, we need to understand that when the current is passing in this direction, very small amount of current is flowing here, because these resistance are very high. These resistance are very high. Okay, this resistance is negligible. So milliamps of current is flowing here. So milliamps of current, if you are saying that it is a 5 ohm resistance, if it is milliwatt, or else it's no, it will, the work will not done here. So only small amount of current. See what is the voltage drop across this, means it is also 0. It's not almost 0. So no work will take place now. Work take place is only if current is flowing in this direction. Because here you can see that load resistance is very small, 5 ohm if you consider. When it is turned on, it will not offer any resistance, or it will not, its resistance is very small, ohmic resistance. So voltage divided by 5 ohm. If it is 230 volt, 230 divided by 5 ohm, that is the current it is flowing. Okay. Now, so it is just principle wise I have given you. So I will explain you using our simulations. Okay. I'll go to simulations. So in this we learn how to use how to make circuit using PSpice also. Go to start, OrCAD capture CA slide. Okay. And then file, new project. Give some project name or file. Or triggering circuit. See here, you should click this analog or mix ready. You should select this. Here there is a browse option. I have kept in E drive. Okay, if you want to keep in any of folder, you keep there. Then press OK. So I think I have already stored such files, so I will give it name or firing circuits. Then OK. Create based upon existing project, or create a blank project. You may create a blank project. Okay. So we got this window now. Place part, place part. See here, when you here you click this. This is an option because most of the files are in the libraries. Okay. You go to this browse file. So we need to select all these files. So control A, then open. This we need to do only initially, only later it won't ask. Okay. So now we can see several libraries are here: eval, valAE, valp, ltspice, sources, sourcestream. Several libraries are there. Okay. See here there is one library called, if you press A it will show you analog library. What are the components in analog library? C is the components, and several things is there. L is a component, so many is there. Op-amp is a component, so much is there. Resistance is a component. Your L, C and R is available in analog library. Okay, and the rest, so many things is there. You can use it, or transformer is also there. So whichever is required for us we are going to use. Only few are required for us. Then one more library, analog library, is very important for us, and one more library is source. So you can search here, or else you just type that name if that name is known to you. Otherwise we need to search source. So there are different sources are there. See here, digital source. Okay, what is our requirement? See, pulse is there, I pulse. These are the current pulses. This is current source. So VAC is there, VDC is there. This is DC voltage. V exponential. V pulse is there. This is also very important. V pulse. We most of the times in power electronics we use it. Then V sine is there. This is we are using. V source is also there. Okay, V sine. Sometimes we use V sine. Okay, I will write V sine. This is one important thing, correct? Sine, source voltage. You just press enter so that you can drag here. Then what is the next component in our slides? We can see here. So it is a load. Load means all resistance. So okay, see here, analog library, R, so R, press OK. Once you press OK, one resistance is here, one more is I require, one more I require, yes. And one more component which is required, yeah, I will tell you, thyristor. It is in eval library, so I knew that. That's the reason I will type eval. Otherwise we need to search all the libraries. See, the first element itself is a thyristor. Okay, second element is a triarc. Several 7400 is there. So many things is there here. Okay, you go to thyristor and press enter. We got this. Okay. Now, so you just right click here. I want to rotate it. I can rotate. If you want to rotate still, yes. Then okay, we'll connect using a wire. This is a wire, this is a wire. So using the like this you can connect, just move it. Then it should be connected to anode, correct? The negative should be connected to cathode. See, what we done here is power source. You can drag this. you can keep there, it's no problems if you want. Okay, so now, so here this is power source. Okay, we need one more ground also. See, please go to ground, place ground. This is very important. This ground you choose it. Okay, source is okay. 0 system ground. Okay. So now my circuit is complete. This is source and this is thyristor. See, this is a main. Okay, if you consider this is a load, so instead of load I'm using resistance. Set on 5 ohm or 10 ohm, I write 10 ohm. I'm considering a load is having a 10 ohm resistance. Remember, always we as an engineer we need to differentiate which is a power circuit and which is a firing circuit. See, this is your source, this is your load. The source is giving power to load through this switch. If there is no switch, what happens? Continuously it is giving power to load. I do not have any control. So if you, here we have kept a switch here. This is a semiconductor switch, correct? No? It is SCR. So if you apply a gate pulse to this, then only power goes from source to load. If you don't apply gate pulse to this, the power not goes from source to load. That is the meaning. So how to generate that voltage which is required here? To generate that voltage, one more circuit is required. That I need to implement here using few components. Okay, we'll rotate right. There are several rotation, rotate, right, left, mirror image, so many things, mirror vertically and all, which that you can learn. You just learn one by one. This is for aligning all these things. Okay. Usually one resistance is enough. Okay, I will connect that one more resistance later. Okay. So again you connect using this wire. Okay. So you can write this as, let's see, write this as 5K, 6K. This is 1K values. Okay. Then make it 10K. I will make it 10K. I'm just checking trial and now. So we need to apply gate pulse here. Correct? Strictly speaking, this is the way we need to do it. This is very simple. Yeah, later we'll alter it. So to add some more complexity. Okay. See, what we did here is, this is my power circuit part. Yes, I have connected to resistance. Why exactly? I will tell you. Okay, what is a power source? See, this is our V off. That is an offset voltage. Here we are not giving any offset. Offset you make it 0, or you just write it 0 only. Or else if you keep it blank also, nothing happens. Amplitude. For a 230 volt RMS, amplitude is 325. But remember, this is our student version. It is not supporting all those higher amplitudes and all. It is supporting only lower amplitudes. Okay, so I'm just writing 50. Assume that I'm writing that from 50 or something. What, you are having a problem? 50 volts. I'm saying that 50 volt is an RMS. Okay, so not an RMS, it is amplitude. If you are writing that in RMS, means if any voltage like 230 voltage means 325 is a amplitude. If I am representing the 230 volt supply, then I should write here 325 or point something. That as that value I should write here. Otherwise, I can keep this blank. Okay, and I can write here 230. Both are working. It will take both option as given. Okay, so this I should keep it blank only. Right here 50. Okay. So frequency is in India it is 50 hertz. That's the reason I will write 50. So I will repeat. See, we have taken this from V sign. If you are having confused, V sign, you go to source library. There you search for V sign. V sign. This is V sign. Press enter. We got this. You just got it. Okay. So what are the things I need to change? Amplitude. It just I'm writing amplitude as 50. That is a peak. It may be max. Frequency 50. Frequency 50. Offset is 0. Offset is 0. Not any offset. Okay. Next. Circuit is over. We'll check what happens if I write these circuits. So then this is a circuit. Then I should write PSpice new. This is for simulation. Some names you should give. Triggering. Any name you can give for this simulation. It is asking you run to start saving data after. Means see here there are different analysis method, time domain, DC sweep, AC sweep, bias points and all. We are going for time domain right now, and this is parametric sweep. Those are all different. So this is, you select general settings. Oh, don't go for this. That you can do it later when it's required. General settings. Then this you can skip initial transition bias point. This you can, and if you enable this initial transition things, or bypass it. So now start saving data after 0 seconds. So if you want to start view the output from beginning 0 means beginning from the origin, in the sense beginning. So it is, you will see 0 seconds. Then run to, so 50 hertz. How many cycle I want to check? So assume that you want to find out 10 cycles. 50 hertz means 20 millisecond is period. 10 cycle means 200 milliseconds is giving you, so 10 cycles of output. If you want to check 5 cycles, 100. If you want to check only 1 cycle, 0 to 20. Half cycle, 0 to 10. Or if you want to view the output from second period, second cycles to 10th cycle, 20 millisecond to 20 milli to 200. That's all, from some starting point till end point. This is starting point, this is last endpoint in time axis. This I want to check. Here you can check write 0, apply. Okay. See here, when you start simulation, you got several options here. So in these options, we can check. You can observe the voltage. So this is a probe like structures. This is we are using to. There are plus and plus is there. So in between 2 points, if you want to view the output, we can use this. Okay. So I will check the load voltage. Okay. So otherwise initially we'll go for source voltage. Okay. If you want to check the source voltage like this, you can do. And one more option is also this is also voltage, but it is always with respect to ground. So here, if you keep here, it is giving the voltage this point, and this is a ground anyhow, correct? Here I can use it. If you want to observe the voltage this point and this point, I can use this, and here also I can use, because this terminal is ground, I can use this. But here it is not useful, because if I write here, it is giving you this point, and if you want to observe the output in between these 2 points, then I should go for this only. Okay. So anyhow, initially we will check the output voltage of this only. Initially. Okay. So you just run it. See here, this is my input voltage. It is starting from 0 and going till 50 volt, coming back like this. So what is the time period? 0 to 20 milliseconds. This is my input voltage. This I want to deliver to my load. Okay. So this is anyhow only one source, one load resistance, one SCR is there. Only first half cycle we are trying to deliver to load. Okay, we'll check whether what is an output here. You just keep this probe here. Run once again. Yes. See, whatever we have got red is an output. We got that output. Okay. So for clarification, I will remove this so that you can see here. Okay. This is whatever I have shown here is how many cycles. See, from this is 0. This is 20 milliseconds. From 0 to 10 milliseconds, my output voltage is there. Correct? Not from 0. From some points to here it is there. Okay, we need to investigate why it is starting from this, why not from 0, everything. Yes. So I can see here that simulation edit profile. If you go here, if you want to check only some few cycles, if you feel that 200 these many cycles is very it's too much for me, if you want to check only few cycles, you just tell me 20 millisecond. If you just check 4 cycles, means till 80 milliseconds will go for 4 cycles. You can apply, press. Okay. And then run. See here, it is giving you only 4 cycles. Okay, it's good for me for analysis. 0 and it is giving 10. Okay. So you should ask a questions now. Why, sir? Okay, why second half cycle is not existing is common, because in the negative half cycle, okay, I can show you here. See here, if I show both, whatever you just keep this in mind, whatever is observed here is input, whatever red is output. Okay, red is output. See, my input is when in the second half cycle, what is negative half cycle? The output is whatever it is in a red is 0. Why it is 0? because in the second half cycle this point is negative and this point is positive, means the anode is much negative compared to, is more negative compared to cathode. So automatically J1 and J3 is reverse bias. So this will turn off. This will turn off. Okay, I will tell you. Next, I said already, to turn on an SCR some gate voltage is required. From where I got the gate voltage? See here, this terminal is connected to some points here, some points here. Okay, okay. Next, see here, I will just move it. We will check what is the voltage here, what is the voltage developed here. What is the voltage developed here? So we will put some points here, voltage points here. See, you use simple Ohm's law. As I told in the beginning, in the first, as soon as you start this circuit, this will not turn on, because I am telling you. So current will flow in this way. Current will flow in this way. Just after zero crossover. Just after zero crossover. You will check here. What is the voltage? Okay, I will remove this voltage. I will just concentrate on this. If the current is moving in this direction, means there should be a voltage across this resistance. Why? What is the voltage? Current into resistance. If current is passing, means voltage should be there. We'll check what is the voltage here. Okay. See, this is a negative half cycle. Yeah, negative half cycle. In the positive half cycle, what happens? The voltage will increase. See, you can see here, the voltage will increase. This is 0, this is 1, this is 1, 2, 3, 4, 5 is there. 5 in the sense it is 0.2, 0.2, this is 0.2, this is 0.4, 0.6, this is 0.8, nearly 0.6, 6.5, 0.65 voltage. The voltage sinusoidally it is increasing from 0 to 0.65 or 0.7. As soon as it reaches to that point, 0.7 volt, what happens here? This is what is happening here in the gate. Okay, what happens? So that 0.7 volt is enough to turn on this SCR, in the sense, so because of that 0.75 voltage, enough number of carrier is injected to the gate terminals. Yeah, if you want to view the gate current, you can see here, you can connect here a current. So we can see here what is the current which is flowing to the gate terminal. Okay, so I'll run this. Okay, because this is showing you in dimension wise, because voltage is too much because of current, so current is very small. Okay, I will remove these voltage points. You can see here. Okay, see here, this is a current. What is a current? See, current is also, it is in 0 amps initially, just after zero crossover it went till 1, this is 1 amps, this is 2 amps, 1.5, nearer to 1.9 amps it went. So remember, my voltage is sinusoidal. Because of that, when sinusoidal voltage is applied to this circuit, the current is which is flowing in this circuit is also sinusoidal. Correct or not? The current is sinusoidal. This is an exact input current. I can show you. This is an input current. Whatever current is totally flowing in this circuit. Whatever current is flowing in this circuit. I can show you all these currents. You can hear. See, whatever current is flowing in this circuit I can show you. Whatever sorry. Okay, now I will not show the voltage right now, I'll just change you the current. So we said that okay, you just go through everything whatever I mentioned. So see, this current is too much. See, 4.5, this is nearer to 5, that's the reason it is showing in, it is in milliamps, so we are not be able to observe it. Okay, so anyhow I'll just concentrate on this. So the current is reaching till 1.9 milliamps. Till current reaches to 1.9 milliamps, this SCR is in off state. This SCR is in off state. So the main current, the entire, because of this voltage, current is flowing in this path only. So it is okay. Why current is sinusoidal? You should ask a question. Why current is sinusoidal? Voltage is also sinusoidal. That voltage Vm sin omega t, it is varying like that. Vm sin omega t divided by total resistance. What is the total resistance of this circuit? Total resistance of this circuit is 10k, 1k, 11k, yeah, 11 point something, 11.0101 k, 11.01k. So 50 by amplitude, at the peak amplitude is 50, it is starting from 0, going at 90 degree, it goes to 50 and coming back to 0 and going to minus 50, coming back to 0. This is an amplitude we have applied here. In that way only, that divided by this total resistance, current is varying. But once we have studied in SCR, some amount of carrier we need to inject to the gate terminal so that it can initiate the turn on process. Means for this SCR 2N1595, in this simulation what we understood, how much amount of current is we need to inject to the gate to turn on an SCR is nearly 1.9 milliamps. If I supply 1.9 milliamps of a current to the SCR, it will turn on SCR. Okay, so to supply 1.9 milliamps of a current, how much voltage is required here? How much voltage is required here? How much voltage is required here? That we can see here. So how much voltage is required? Whatever shown in the red, green is voltage. What is voltage is required? This is 0. This is 1. This is 0.5. This is 7.5. This is 6.25. Nearly 6 volt is required. Correct, no? See, 2, 4, 6, 6.5 voltage is required. 6.5 voltage is required, should be generated here. 6.5 voltage should be generated here. Then it gives you 1.9 milliamps of current to this gate current. Then SCR will turn on. Okay. So yeah, a lot of things we need to understand here. Okay, this is okay now. See, then why this circuit? Okay, can you see one's output voltage? You see here, when what is a time axis, or okay, I will go to current. See, this is in time axis, this is 0 to 10 millisecond, it is 20 milliseconds. When exactly my this 1.9 milliamps of the gate current has reached to 1.9 milliamps? Because why gate current has from who has given the gate current, who is which component is responsible for gate current? The voltage, this resistance totally, and these two resistance, and voltage which is developed across this is causing this current, correct or not? Causing this current. Okay, so for these particular components, for this of 10k and this of 1k, 1.9 milliamps of current is flowing here. When exactly this is 5 milliseconds, this is 4 millisecond, or very nearer to 3.99 milliseconds. This is 5 millisecond, this is 4 3 2 1 to 1.9 milli, and nearer 1.9 milliseconds. At 1.9 milliseconds, so this is by chance it has come like this, 1.9 milliseconds, 1.9 milliamps of current is flowing. 1.9 milliamps of current is flowing, and it is turning on the SCR. Why I should say that it is turning on the SCR? How can I say that it is turning on the SCR? Okay, one thing will you check here, why I am saying that it is turning on the SCR. See here, if you check the output voltage, see, till this is 5 millisecond, this is 1 millisecond, 2 millisecond, till 1.9 millisecond there is no load voltage. Why there is no load voltage? Load voltage is very small. I am saying that no load voltage. Why? This SCR is in off state. If this SCR is in off state, the current direction is only in this way. It is only milliamps of current is flowing here. Milliamps of current into this very small voltage is dropped here. So I can say that if the SCR is in off state, no current is flowing. Exactly, it is almost same, no current, but current is flowing, but no work will take place. So small amount of current is flowing. So this SCR is in off state. But at 1.9 milliseconds will turn on the SCR, because the in each time the voltage is developed here. Starting from 0 crossover, the voltage is developed, but whatever voltage initially developed, it is not enough. Exactly at 1.9 milliseconds, some voltage is developed here, and it is enough. Something 1.9 millivolts. Exactly at 1.9 milliseconds, some voltage is developed here, and that is enough to cause 1.9 milliamps of current here. That 1.9 milliamps of current is enough. That is the minimum gate current required to turn on the SCR, and it will turn on the SCR. That's the reason 1.9 millisecond onwards till 10 millisecond means my period of a power is 50 hertz. So total period frequency is 50 hertz. Period is 20 millisecond. Half cycle is 10 millisecond. So here the SCR will turn on at 1.9 milliseconds, and it will continue till 10 milliseconds. Okay, that's the reason this load will receive full amount of current from 1 milliseconds to 10 milliseconds. We can observe here, is it correct? Yes, see here, it is receiving the voltage. Once the current comes, voltage is developed, okay, from 1.9 milliseconds to 10 milliseconds. Then after 10 milliseconds, why it is not receiving till 20? Because the input voltage takes negative half cycles, becomes negative half cycles. It is a negative half cycle. So negative half cycle J1 and J3 is reverse biased. Again, in the next half cycle, why it is not receiving any current, and why voltage is not existing across load? Because the whatever voltage is developed across the resistance, across this resistance R4, is not enough to give the gate current, that is minimum is 1.9 milliamps. So SCR is in off state. SCR is in off state. Once again, the gate current becomes 1.9 milliamps. So SCR will turn on. Okay. I think I clarified this right now. So listen here. This somebody says that, sir, this voltage I don't require. I require still less voltage for SCR, means to the load, means I should supply still smaller voltage to the load. How to do it? Means we require voltage from somewhere here. This is, what is the degree? This is 0, this is 180 degree, this is 90 degree, 9, this is 1 2 3 4 5, means 18 degree, this is 36, this is nearer to 34 degree. Somebody says that I require firing angle more than 36. How to do it? Okay, so somebody says that I require firing angle of 90 degree. 90 degree means my SCR should turn on only after 90 degree and it should continue till 180 degree. Only from here to here I require voltage. We'll try it. Okay, this is a circuit. See here, 1.9 milliamps. So for these components 10K and 1K, we got 1.9 milliamps at somewhere at 1.9 milliseconds. That we called as 34 degree or something, because 10 millisecond is 180 degree. So he is saying that the firing angle should be moved towards 90 degree, means I should give 1.9 milliamps of gate current at 90 degree. 90 degree means 5 milliseconds. 90 degree means 5 milliseconds. Means after 0 crossover till 5 milliseconds, the current which is given to the gate terminal should not reach to 1.9 millivolt. Only at 5 millisecond, the current which is flowing towards gate should equal to 1.9 milliamps. Okay, what to do now? So shall I increase the currents or shall I decrease the current? Because voltage whatever developed is the product of current into voltage. Whatever current is flowing, it is giving the sufficient, it is generating sufficient voltage, or it is generating the sufficient, because when sufficient voltage is generated here, then only sufficient current flows here. Correct? So after some more time, after some delay, some voltage should be generated here that is enough to cause 1.9 milliamps of currents to this. So we need to add one more delay, means we need to do such arrangement. So we should reduce the current. To reduce the current, how can I reduce the current which is flowing here? This is a load resistance. It is we are not changing. It is an appliance resistance. If it is some any DC appliances, its resistance. I am not altering that appliances which I purchased from the shop. Okay. So this is my circuit elements. This I need to change. So shall I? We can once again, you can go back and check your waveforms. See here. Right now it is it. So this is 5 milliseconds, this is 2, this is 1, 2, near below 2, it is at 1.9 or 1.9 milliseconds somewhere here. We need to drag this edge, we need to move this edge towards this 5 milliseconds. So means see here, right now the current, this is a gate current, is reaching 1.9 milliamps exactly at 1.8 milliseconds or 1.9 milliseconds. So now I should slowly I should means this point should come somewhere here, means the current should increase in this way, so this points should come here. Slowly current should reach to that value. How? We'll increase this 11k, we'll make it 11k, so current I should reduce. See, earlier it was at 1.8, now it is 2. Okay, still I should increase. I will make it 14k or 15k, we'll see it. See, earlier 1, 2, 3, I told 5. So 15k, make 18, 17k, 18k. So this is just here only, near it. Still I should increase. K. Is it possible? It is nearer to 4. We'll make it 40k, 33k, 39k, 39, it is 4.5. So 44k, 54k, still it is 4.5 now. Make 60k, 63k, 70k, 80k, 85, 95, 99, came 20 30k. Still 140k. Correct. So 155k is enough. It is now, it is coming nearer to 90 degree. One 50k. Okay, listen. So 168k we have got it. See, this current has reached to how much amps? Here it is 200, bit more than that, microamps. 200. This is 200. This is 300. This is 200. 220 something. That many amps. So that amps of current is enough to turn on SCR, and SCR turned on. Okay. Now remember, the voltage whatever generated here, see here, if you go to this, see exactly at 5 milliamps, whatever voltage generated across that resistance has reached peak, means that is nearer to same 0.75 volts, 0.75 volts, or same voltage is CT, it is 50, 60, 70, 0.75 volts. And once it 0.75 volt is reached across that resistance which is connected across gate, that is enough to turn on the SCR, means that gate whatever voltage you are given to the gate and cathode, that is enough to turn on the SCR, and that will supply the enough currents to gate terminal, it will turn on. So only requirement is we need to generate that minimum voltage whatever across that 0.75 something for this, but this is only for this SCR, that much voltage what I should generate here, so that I should supply the currents which is nearer to 1.8 or 2, in and around 2 milliamps, 1.2 milliamps of current, 1.9 to 2 milliamps of currents. Then I think you understood the logics here. So we are passing a current in this. Okay, as soon as this turns on, what happens to this currents? See here, the current is coming here. This is turned on, means this is acting like a short. This is a low resistance path. Entire current is moving in this way, and no current is moving in this way here onwards until this SCR remains in on. Then when exactly once SCR becomes off, when in the next second half cycle, negative half cycle, whenever it begins, SCR once again turns off, once again the current starts flowing here. Current starts flowing here. Until that, the current which is flowing here is zero. That's the reasons only till SCR turns on, the current is moving in here, and once the voltage whatever developed here is enough to turn on the SCR turns on, then all the current is moving in this direction. No current will move in this direction. See here. So that's I can show you the current axis only, current axis. So when voltage, see, when the no current is flowing here, no voltage is developed here. That is the reason this green color, see, the voltage which is developed here is very small. As soon as here till here it was see, it went till 0.75 volts, then it becomes very small value. Okay, so I can show you in the current, it is very small. Okay, it is, you can consider as a zero also. Okay, if you just show the current only, you will understand. See here, the current is moving only whenever there is a voltage drop here, otherwise there is no current here, correct? Yes. So because if there is no current is coming in this path, there is no question of current which is flowing here or flowing here. Okay, so all the current is flowing in this direction as soon as it turns on. Till turn on, this circuit is required. Once it turns on, this circuit is no longer required. Okay, so here what happens, as soon as it turns on, all current will move here, so this current becomes zero only. Whatever, this current itself is zero, then obviously this current is also zero, this current is also zero. So you can see here, see this current till this nearer to 2 milliamps, 0.2 milliamps. So current is flowing as 0.2 milliamps, sorry. So when this is exactly at near to 5 milliamps in my circuit, SCR will turn on, so no current is moving in that direction, so no gate current is almost zero. So okay, see here, if you consider voltage here, this is a voltage, this is input voltage, this is a voltage which, because in PSpice see, all are shown in the same scale, so it is not visible. So this is my input voltage, and this is my load voltage. Whatever it is shown here is load voltage. See, the input voltage and load voltage is very high when you compare to gate current and whatever the voltage which is connected in between gate and cathode. So it is not showing you. I can multiply this and show you. This is load. This yellow current is voltage. See here, I just multiplied it, just to zoom it. See the voltage, and I can show you the current also. This also I am just zooming it, I am just multiplying you and showing, because it is very small, so it is not visible. So I can show you. Okay, both windows will show you. whatever shown here in a blue color is an input voltage. See here, input voltage. Whatever I have shown here is load voltage, load voltage, load voltage. The load voltage begins at 90 degree here, 5 milliseconds. So if I remove here this can show. Okay, then so whatever I have shown here, this is the voltage which we have connected to gate and gate no voltage. This is yellow color. See here, the voltage is also sinusoidally developed and it will reach to this value. Means what is this value? This is 50, then this is 10, sorry, this is 10, 10, 10, 10, and this is nearly, in this case it is saying that 7.5 because I have multiplied by 10 already. I have multiplied by 100. So it is 10, it is showing you 7.5. Multiplied by 100, you just divided by 100. What is that? 7.5 divided by 100. That many voltage. Once that voltage is reached, then only the current which is flowing here. As you can see here, current axis. So I will remove this. Current is very small, that's the reason still it is not visible. So I will again multiply by 1000. Still it is very small. Okay, I will just remove this voltage axis and all. You can see current. I can see this current is also, I can remove this. Okay, so current is reaching to here, then it is becoming 0. So this is the way it works. This is the way it works. Okay. So what is the meaning here is current is flowing here, only it turns on. Okay, I think I clarified all your doubts. So this is an arc firing circuit. If you want to reduce this firing angle, so I'll just here onwards I'll just show you only the load voltages. Okay. Here, see, if you want to reduce this firing angle, this is exactly 5 milliseconds. You want to reduce this, what we need to do? Last question, should reduce this value. Make it 20k. Make it 20k. Yeah, firing angle has moved towards this. So in this way, we can supply a controlled voltage to the load. So if you require more voltage, we should keep this firing angle nearer to this. Assume that full voltage is required for me, and see here what happens. I will reduce this to very small value. See, it is almost acting like your diode rectifier. Means in the beginning itself we have given enough current to the gate terminal, so SCR will turn on in the beginning itself. So entire half cycle is passed to your load. Okay, thank you. One of the problem in this circuit is, you can see here, for some, see here I have shown this is for some, for once some firing angle. I will show you the output voltage first. Okay, see here, this is an output voltage. This is an output voltage. See, this is an output voltage. This is an output voltage. Yeah, firing angle we have chosen somewhere at 90 degree. Okay, no problems. Okay, we understood. No? Okay, we'll check. What about gate current? So this is a gate current. So gate current somewhere here 90 degree. It is reaching, means how much gate current is required to turn on SCR. That is reached somewhere around 90 degree, means nearer to 5 milliseconds. Then once SCR turns on, no gate current flows. Yes, but in the negative of cycle, what happens? You can see here the negative of cycle, this is in off, so current is moving in this direction. So some amount of current is moving in this direction because here there is a resistance. So that's the reason some in negative of cycle also current is moving towards gate terminal. So if you check the voltage here developed across resistance R during that time is also, you can see here, yeah, when I show this voltage, voltage is this red, this is current is very small, that's the reason we are not it is not visible. So we just magnify it just by multiplying by some 100. I just magnified that current, so it is visible for you now. Okay, see here the voltage is also sinusoidal. So at that point, once gate voltage, the applied gate voltage, which is the voltage which we applied to gate terminal, if it is reaching somewhere nearer 0.8 volts, then SCR will turn on. Then later onwards, SCR completely turns on. SCR completely turns on. No current flows in this path. No current flows here. No current. Entire current flows in this path. That's the reason no voltage here. No voltage here. This we are observing here. This we are observing here. No voltage. It is zero and no current. No voltage and no currents. But the negative of cycle, what happens? When the input voltage takes negative, so this will turn off because J1 and J3 will reverse bias and J2 will forward bias. J1 and J3 reverse bias, so this will turn off. Once this is turned off, the entire current is moving in this direction. So again, that's the reasons you will find negative voltages and a negative current in this direction. See, negative voltages and negative currents. But problem here is when I am explaining the SCR, I said when SCR is in reverse biased condition, because it is in negative of cycle, so this is more negative than this, because the negative of cycle anode is more negative than cathode. In this time when J1 and J3 is reverse biased, we should not inject any carriers towards gate, because if you inject, it may break your SCR, it may break down your SCR may get damaged. So remember, when SCR is in negative reverse bias, means when anode of the SCR is made negative compared to cathode, in that moment we should not inject any carriers to the gate, but this circuit does it. But why it is, this is a simulation, so that's the reason it is not get damaged. So if it is a real circuit, so there is a chance that this SCR may get damaged, because you should keep in mind, whenever SCR is in reverse biased condition, means an anode is made more negative than cathode. At that moment, we should not apply any voltage to the, we should not apply any inject any carrier to the gate. So this circuit we should alter such that only in positive of cycle it should inject a carrier till it ons to turn on. Negative of cycle it should not inject. So what is the solution? Solution is very simple. So go to place, part, so you check eval library. So we should connect one diode. So what I'm doing now here, I'm searching for diode. Okay, if I have a diode, I can give solution for that. You may be knowing what is the characteristic of diode. Diode is it allows only in it conducts only in positive means when anode is made more positive than cathode, and again only in one direction electrode levels current. So this in this circuit in positive of cycle, any whatever voltage developed across R4 is positive at the time in positive of cycle. Here you will get more positive anode of this is at higher potential compared to cathode, so it conducts. So in negative of cycle what happens? So this is connected to negative potential, so it is acting like a reverse bias diode. It will not allow any current flow. So if you see here now, if I run this circuit, you can see here I will show you the current is now this is, so we'll just magnify and show you. Because a little more lesser because the diode drop is there also there, so we should give some more current, more voltage should develop across a R4, because it should compensate that 0.7 volt is required for this. So once this circuit see, now you are getting the same firing angle for this value nearer to this 55. Because you cannot see, because now I require more voltage here, because first I should forward bias this. So 0.7 whatever voltage is there here, the 0.7 voltage is dropped here, remaining voltage is used to inject a current to the gate, means remaining voltage will be applied to the gate and cathode terminal. That's the reason some 0.7 voltage drop exists. See, we have used this diode to block the reverse current, but it is causing some problem. Why? Because in a forward, while it is passing a forward current, there is a drop across diode, that is 0.7. So some here now onwards we should give some extra voltage from here, so that 0.7 is dropped also, then also should remaining should able to turn on this. That's the reasons I reduced this as soon as I this. Okay, I think that's you will understand, you can need to understand. Okay, so this circuit is okay, good. Now it will see here, if I show a current only, I can show you the current. See here, see here, yeah, I will just multiply this current axis by 100. Okay, see, the current in positive of cycle, the gate current is passing, but once it turns, SCR turns on here, as usual that current will become 0 till 10 millisecond. Then after 10 millisecond till 20 millisecond, yeah, whatever voltage across your resistance R4 is changing to negative, but there is no current here. There is no current because this diode will block that. This diode will block. So no current here. So see, that's the reason. So see here, you can see here, yes, only from 0 current pulse is applied. See, this looks like a current pulse now. Okay, so this is how, so that we are not given any current pulses to the gate during the negative 10 to 20 millisecond in the negative cycles. Yes. So if I show this with respect to input, see here, this is your input voltage, and this is a green color is a current pulse. Green is a current pulse, but it is again, it is very, because I should magnify it. See here, you can see here. Very small it is, current pulse, it is very small. Okay, because I magnified so that it is visible to you now, otherwise it is not visible. So this is the current pulse, and this is your input voltage. This is your input voltage. So if you see this output voltage across the load, this is your whatever is showing like this here. This is an output voltage. This is output voltage. Red color is input, green is output. This is green is current pulse. This is output voltage. I can show you one after another. So I think input you no need to yes, no need to you see. This is our output voltage. This is our current pulse. As soon as current pulse reaches to that required value, which is enough to turn on the SCR, thyristor will turn on, so load current starts flowing, so load voltage will observe here from that point onwards till the end of the half cycle over. Yes. So one problem we have solved here, and there is one more problems. Okay, can I move this firing angle till 90 degree? We have moved here. See, whatever 60K I am using here, this, what is the firing angle? Okay, I can show you now onwards. You will understand what is the firing angle means. The moment the current reaches to that minimum value, or moment the SCR turns on. So I can see here, I'll show this current. Yes, see, is it possible to move this beyond now around it is 5 milliseconds? Can I see if I reduce this to 10K, what happens? Yeah, it will move to left, correct? Left, correct. Then if I move to this to 65, what is the earlier value? 65K. Firing angle move is around 90, exactly 90. In 64, I will make it. It's not enough. Key. But problem here is 62 and all, if you use it, it is almost 90. Problem here is if I want to move this to 130 degree after 5 milliseconds, it is not possible. See, if you still increase, if you just increase to 70, no, problem is SCR won't turn on only. See, SCR has not turned on. See, there's a big here is no chance. So what happens here, you can see here when exactly SCR has turned on to this here, somewhere here. So this problem why occurs, because we cannot move, because here yes, this is a sinusoidal, whatever voltage we are developing. Okay, this cell 62, 62. We'll magnify it. The firing angle we cannot move beyond 90 degree, because for a 61K 90, it is almost around 90 degree. See, 200 microamps of current, a little more than 200 microamps of current is required to turn on. So you can say that it is 220 to 40, 220, 202, I can say 202 microamps of current is required. See, if you increase this, there is no point of reaching that value, because that, see, for a 61K in sinusoidal it is at 90 degree input is in peak usually, correct? Input is what is an input actually? So input is in peak at 90 degrees. So you can see here, that is my I connect here this, so if I connect this here input, see, if I connect this input, see here, the input is taking peak at 90 degree, 90 onwards it is decaying. So if you increase the resistance, what happens? My intention is what happens? current will not reach to that, because after 90 degree the input is reducing. Resistance is a Ohm's law. When input reduces, current also should reduce. So no point of reaching to the value which is required. See, I can say so it will never reach to come beyond this below. So what is the problem here means, if you set for, it is not possible to set for more than firing angle more than 90 degree to 180. You can set the firing angle for 0 to 90 only. It is not possible to set the firing angle more than 90. There is a drawback of this. We need to overcome using RC firing circuit. That we will study tomorrow in the next class. Okay.